In the last video, we looked at survival analysis for a single survival curve, and in this video we're going to extend that to looking at comparing two different survival curves. So the example that we have is on tumor genetics. So there's patients here that have individuals with a different subtype of cancer. One is the basal subtype and the other is the luminal A subtype. And so let's just take a look at the data here. So here's the subtype, so either luminal A or basal, and then we've got the overall survival in months, and then status, it's 1 if the individual died, and it's 0 if the individual left the study. So we don't know the eventual outcome. All we know is that this person survived to 4 months, and this person survived to 9 months, and so on all the way down. And these two at the end both survived to 92 months, one with luminal A, one with basal. So we'll use the survival package again, and first thing we need to do is to convert the data into a format so that we can use the survival package. So we do that with the serve function, and then we use the serve fit function just as we did before to estimate the Kaplan-Meier survival curves. And then we'll use ggservplot to draw the two survival curves together on a single plot. So the red survival curve is for the basal subtype, and the yellow one is for the luminal A subtype. So it appears from this graph that individuals having the basal subtype have a worse prognosis, in other words a poorer survival, than subjects having the luminal A subtype. And so this is useful information to know because there might be different treatments that would suit the different subtypes. So we talked in the last video about how these curves are estimated, so I'm not going to repeat that here. We also talked about one number that's interesting is the time at which survival drops to 0.5. So if we trace along 0.5 here, it hits the red curve around here. Looks like about 30. We don't actually hit the yellow curve, so we can confirm that by printing the survival object. And so under median we've got 30 days, not 30 days, 30 months for the basal subtype, and not available for the luminal A subtype. That's because when we trace 0.5 here, we don't actually hit the yellow curve. The yellow curve doesn't drop to a survival of 0.5 within this time period. When comparing two survival curves, one value that's of interest is the hazard ratio. So the hazard ratio at a specific point in time measures the hazard rate in one group relative to the hazard rate in a second group. And so the hazard rate that it's talking about there, the hazard rate at a given point in time, is the instantaneous rate of death of subjects who have survived up to that point. So we talked about hazard ratios previously when we were looking at 2x2 contingency tables, and so it's essentially the same idea here. So we can go through some hand calculations, and again this can be useful to learn in a little more depth what the various quantities are measuring. But in practice, you wouldn't do these hand calculations like this. So this is purely for learning. For practice, we can instead use the servdiff function and pick off these four numbers here. So D1 is the observed number in the, looks like the basal group. So it's the observed number of deaths in the basal group, and D2 is the observed number of deaths in the luminal A group. And then E1 is the expected number of deaths in the basal group, and E2 is the expected number of deaths in the luminal A group if there's no difference between the basal subtype and the luminal A type. So these are the two values that would be expected for the number of deaths if there really was no difference in the survival outcomes between the two different subtypes. And so if we combine these numbers in this fashion, so D1 divided by D2, all divided by E1 divided by E2, and that gives us the hazard ratio. So the hazard ratio in this case is 4.34. And so what that's telling us is, so this is the hazard ratio of the basal subtype relative to the luminal A subtype. So in other words, that's telling us that the estimated hazard rate in subjects having the basal tumor subtype is more than 4 times higher than individuals having tumors of the luminal A subtype when we average over all time points in the monitoring period. So that's one way of summarizing what we can see in this survival curve graph. We can see the prognosis for the basal subtype is much worse, but calculating the hazard ratio is a way of putting a number to how much worse. As usual in statistics, this is just a point estimate, and so it's nice to be able to quantify our uncertainty using a confidence interval. And so we can run through these calculations here to calculate a confidence interval. And we end up with a 95% confidence interval between 1.38 and 13.64. And your reaction to that might be, well, wow, that's a really wide interval. And the reason is because we've got a fairly small sample size here. We've got a sample size, how many people did we measure? We're looking at tumors. We only have 46 individuals in this data set, and we only observed 9 deaths in one group and 4 deaths in the other group. So there's not a lot of information here, so it's not surprising that this interval is so wide. Finally, we can do a hypothesis test here. So this is known as the log rank test, the log rank test, if I can get my words out. So let's just run through that. So it's a hypothesis test, so we've got our usual 4 steps. First step, state the hypotheses. So the null hypothesis is that the survival curves of the two groups are the same, and the alternative hypothesis is that the survival curves are not the same. Second step is the test statistic. So we can calculate that by hand, and it's based on those observed and expected deaths that we looked at before. But rather than doing the hand calculation, instead I'm going to simply look at the servdiff function, and if I apply the print function to that, it'll actually give me this test statistic. So the test statistic is 7.2, and we can see here summaries of our data as well. So we've got our observed deaths and our expected deaths for the basal group and the luminal A group, and putting all that together gives us a chi-squared test statistic of 7.2. And then the third step is to calculate the p-value, or obtain the p-value in this case, which is going to read it off the software, 0.0072. And then our decision and conclusion, step 4, we're going to reject the null hypothesis in favor of the alternative hypothesis because the p-value is smaller than our significance level, 0.05. And so we're going to conclude in this case that the survival curves for subjects with the 2 breast cancer tumor types are different from each other. And that is not surprising given this graph. The red curve, the red survival curve, is very, very different from the yellow one. So this log rank test does rely on some assumptions, one of which is what's known as the proportional hazards assumption. And to assess that, we can draw this graph here. And in this graph, we want the red curve and the yellow curve to be roughly parallel, which they are in this case. If these curves were very, very non-parallel, so let's say the red one went up like this and the yellow one went over here, like totally not parallel, then we wouldn't really have any justification for using the log rank test. But in this case, it's fine, and so that log rank test that we did is reasonable. So that's a brief introduction to survival analysis of 2 survival curves, and so that's where we're going to leave survival analysis in this course. There's a whole lot more to talk about in this topic, but that's beyond the scope of this course.